We're looking at the 2025 Exam 2 paper in the network section, question 18. Francis is constructing a home gym. This project requires 12 activities A to L to be completed. The activity network below shows each activity and its completion time in days. This network has two critical paths. State the activities that are common to both. So in order to find a critical path, you have to do a forward scan and a backward scan. Now, I start usually by putting a box. I have made this video before, but with respect to this question, I'll do it again. And then I start by doing a forward scan. Now, each of these boxes represents the earliest start time and the latest start time. The earliest start time is from a forward scan, and you always take the larger value. Okay. So the procedure is that we start with a 0 because the activities haven't started yet, and then it takes 5 days for A. You could go either along A or B. Now, in doing a forward scan, I indicate where two edges meet because we're going forward, and any vertex which brings more than one edge to it is marked. So that's 2 here, that's 2 here, that's 2 coming here, that's 2 coming here. Now these are the places you have to be careful in doing a forward scan. So 0 and 0 plus 5 is 5. So you could go along C. 5 plus 7 is 12, and 12 plus 6 is 18. Now because it's a place where I have to make a choice, I try and write the choice here. Now I go back to the end of edge A and go along D. 5 plus 7 is 12. I can see that I'm going to make a choice here again, so I write it there. So let's go along B. 0 plus 4 is 4. And if you go along E or F, it doesn't matter, but I'll go along E. 4 plus 3 is 7. Now, as I told you, when you're doing a forward scan, you always choose the larger value. And so that is 12. And then I can continue either from the end of edge G or edge E and D, it doesn't matter. So I'll choose to continue from the end of G because I actually have to make a choice there, which I haven't yet. So from this point, vertex at the end of edges E and D, let me go along H. So that's 12 plus 7 is 19, and you choose the larger value, which is 19. And along J, 19 plus 1 is 20. And along I, 12 plus 4 is 16. And along F, 4 plus 6 is 10. The larger value here is 16. Going along K, 16 plus 4 is 20. Both the values being equal, we write 20. And then along L, 20 plus 5 is 25. When doing a backward scan, in order to get the latest start time, you always choose the smaller value. Now, in order to, because you can see that there are, when you go backwards against the direction of the arrow, you can see that you have certain vertices where you will see more than one vertex coming, one edge coming to that point. So I indicate them so that I can easily choose the smaller value at each of these vertices. So let's go back to the finish, and we always start with making them equal, and then we subtract as we go backwards. 25 take away 5 along L is 20, and then 20 minus 1 is 19, and then 19 along H is 19 take away 7 is 12. Now going back to the end of K, 20 take away along K, 20 take away 4 is 16. And along I, 16 take away 4 is 12 again. And so, actually I, so that's 12. So now if you go along D, 12 take away 7 is 5, and because there's two edges coming towards this vertex, let's go from the end of G. 19 take away 6 is 13, and 13 take away 7 is 6, the smaller value being 5. And then 5 take away 5 is 0. And now we have a few vertices still to complete. So this 12 take away 3 along E is 9. And coming along F, 16 take away 6 is 10, and we choose the smaller value. Now 9 take away 5 is, 9 take away 4 is 5, and the smaller of these two is 0. So if you get 0 on one of your edges when you're doing a backward scan, that usually means that you are okay. So the critical path now is, let's start adding. 0 plus 5 is 5, and all the boxes where both earlier and the later start times are the same is usually a good indication, but I add as I go along earlier start time plus activity time and check to see the earlier start time of the next box. And 5 plus 7 is 12, and 12 plus 4 is 16, 16 plus 4 is 20, and 20 plus 5 is 25. On the other hand, we can go 0 plus 5 is 5, 5 plus 7 is 12, and 12 plus 7 is 19, 19 plus 1 is 20, and 20 plus 5 is 25. Now clearly from this, so the critical path, we have two critical paths, and state the activities that are common to both. So wherever there are two double colors, those are the activities that are common to both critical paths. And as we can see over here, they are A, they are D, they are L. A, D, and L. Determine the latest start time for activity E. Now, the earliest start time for activity E is 4 weeks. Now, the latest start time is, I usually look at the value that I got along that edge when I did a backward scan, which is 9 days. And so, the latest start time is 9 days for activity E. And if you look at activity F, the latest start time is 10 days. That's the value that you got along the backward scan. A lot of students make the mistakes of actually looking at this box in order to calculate latest start time, but please don't do that. The easiest way is when you're doing a backward scan, the value that you get along that edge, because you had to make a choice over here. The value that you got along that edge as you did a backward scan, that is your latest start time for that particular activity. Because if you were looking at this box, you would have made a mistake in finding the latest start time for activity F. Okay, so the latest start time for F is 10 days, and the latest start time for activity E is 9 days. The next question says, which activity has the longest float time? Now, in order to calculate float time, you should know that activities not on the critical path will have a float time. Not on critical path. So, if we were to record all the activities that were not on the critical path, they are B, C, E, F and G. So, B, C, F, E and G, because as you can see, all the ones in purple are the edges along the critical path. So now if I was to record the float time for each of these activities, clearly from what I just discussed with you a few minutes ago, looking at this is the earliest start time for activity B. Now the latest start time is the value along the edge when you did a backward scan, which is 5 weeks. So B is 5. Now if you look at F, earliest start time is 4 and the latest start time is 10. So the difference between the earliest and the latest is the float time, and that is 6. Now if we look at C, the earliest start time is 5, the latest start time is 6, and so that is 1. If you look at G, there's no problem with G because there's only one edge coming off it, whereas if you have two edges coming off that particular vertex like C does, you have to be careful as to take the backward scan value as your latest start time. Whereas for G, earliest start time is 12, latest start time is 13, and that's 1. And I think that takes care of all the activities that we had to find float times for, and we can see that F is the activity that has the largest float time. A, F, G, H and K are the activities that can be reduced, and the maximum number of days that each of these activities can be reduced is given as 2, 4, 4, 2, 1, and the cost involved in reducing these activities is also given. Now we look at the activities that are on the critical path, and they are A, H and K. Now from what we can see, F and G are not on the critical path, and so it would be really not much use reducing them unless we first reduce activities on the critical path, and if that by chance gives rise to another critical path, then we could look at maybe reducing F and G if they are on the new critical path. So let's first not reduce F and G and see if we actually can do any reduction. Now what I can see is that A and D are on both critical paths from what we've discussed in the previous parts of the question. So A has been given as a reducible activity, so let's try reducing that first and see what impact that has. Now if I was to reduce A, it will have an impact at this vertex, this choice. So let's say I reduce A to 3, maximum reduction possible. Then 0 plus 3 is 3. Going along D, 3 plus 7 is 10. So originally it was 12, now it's 10. Now remember that choice is impacted by the choice along E as well. But B is not a reducible activity, so 0 plus 4 is 4. And E is not a reducible activity, so 4 plus 3 is 7. Of these two values, the bigger value is 10, so 12 now becomes 10. Now let's go along C and G. because there is a choice that has to be made here as well. And the only activity that could impact that choice is activity H, because that's a reducible activity. But how much should we reduce H by is determined by the limiting value that we get along here, because there are no reducible activities along that path. Okay, so 3 plus 7 is 10, and 10 plus 6 is 16. So currently we get 10 plus 7 is 17. So we can't reduce 16 any further, so we have to reduce 17 to 16, and we can do that by reducing H by 1 and therefore making it 16. So both the edges now have 16 against them, so this value now becomes 16. Earliest start time for J. Now J is not a reducible activity, so 16 plus 1 is 17. Now let's see what happens to the value along K. So we decided that F is not going to be a reducible activity. So 4 plus 6 was 10. Now I is not a reducible activity, so 10 plus 4 is 14. And so of these, the larger value is 14. Now currently K not being reduced at all, 14 plus 4 will give me 18. So that tells me that I can reduce it by 1 to make it equal to this 17. So K reduces by 1, becomes 3, and so 14 plus 3 is 17. That makes this value 17, and 17 plus 5 is 22. So from what we have done here, the reductions are A by 2, H by 1, and K by 1. So A by 2, H by 1, and K by 1. And that gives me 1,000 here. I've incurred a cost of 1,000 to reduce each day by 500, so 2 days. And this by 300, because H by 1 times 300, and K by 1, which is 100. And that gives me $1,400 expenditure in order to bring the completion time to 22 days. And that saves me 3 days. There are more structured ways of doing it, and one of them is to actually lay out all the original parts. And I have actually written the values that have been given as the reducible amount of time for each of these activities. So when you record all the parts from the start to the finish, these are all the parts and the original time in days to go along these paths is given as well. And the largest value, so we discussed previously there were 2 critical paths, and these were the 2 critical paths of giving the earliest completion time of 25. Now before you continue to do any reduction, what I found was doing a maximum reduction column is extremely useful. Now what is this maximum reduction column? If you look at all the alphabets I've highlighted, they are the values, they are the alphabets that have been given to you as reducible activities. And against the reducible activities, A I've written 2, and those are the maximum number of days they can be reduced by. G is 4, etc. Now if you add all the number of days that can be reduced from that particular path, A is 2 and G is 4, totally adds up 2 plus 4 is 6. So if you, from the original time, which was 24, you take away 6, it will give you 18. So you do that along each path. So in the next path, A is 2 and H is 2. So that's 4. Take away 4 from 25, you get 21. So when you do this for each and every path, the maximum value that you get is 22. Now that is an indication that you can maximum reduce this particular network by 3 days, because 25 was the earliest completion time. Now the new earliest completion time is 22, and the difference between them is 3 days. So if you reduce more than 3 days, that means that you have made a mistake. So having a maximum reduction column is really useful. Now, how do you go about deciding which activity you're going to reduce first? I usually choose the activities that are common, that lie on the critical path. You can always start by doing the cheapest one. I've started by doing A because there were 2 critical paths and A lay on both. And this is done 1 day at a time. Some people do it more than one, but I find doing it 1 day actually helps me be more careful. And so if you reduce activity A by 1, the paths that will get affected are the first 3 paths. That's this one, and that one. A does not occur in the other 3 paths. So 24 take away 1, 25 take away 1, 25 take away 1, and the rest remain the same. Now in this new column, the earliest completion time is 24 along these 2 paths. Now the objective is to make the old critical paths the critical paths again with the maximum reduction possible. Okay? Now both are 24, but we know that we can go down to 22. So I choose A again by 1, and we know the first 3 paths will get affected to 22, 23, and 23, and the remaining stay the same. So again, if you look at this column, these 2 paths are still the critical paths. But we know that it can go down to 22. And so we look at any other activity that is on the critical path. We know K is on the critical path. And if we reduce K occurs on the 3rd path here, and K occurs here, and K occurs here. So those values will go down by 1, and the remaining stay the same. So now we have got the new critical path to be 23. But we know that originally we had 2 critical paths. Now obviously that implies that 23, the other critical paths already reduced to 22. So that's good. That's what we wanted. Now we have to reduce 23 by 1 in order to bring that down to 22 as well. And the only path that we can't touch A because we've already reduced it by 2 days, but we can touch H. So we reduce H by 1, and that brings the old critical paths down to 22. And that tells you that you can reduce A by 2 days, K by 1 day, and H by 1 day. And so if you multiply the cost involved in this reduction, it's 1,400, which we got previously. Another alternative method of doing it is record the critical paths, the original times, and these are obviously the maximum values. So earliest start times, which is the minimum completion time. We do the maximum reduction possible, as I explained previously, and we have this as 22. Now what we do is we only consider the paths which have the total time greater than the required reducible activities time on the critical path. Okay, I don't know if that makes sense, but if you look at what I've written, the maximum reduction here is 22, and 22 is less than 24, and so we actually can reduce something along this path, and the activity that we can reduce is A by 2. Now on the next path, 22, maximum reduction is less than 25, which was the original time, which means the difference is 3. Now A can be reduced, okay, so which and has already been reduced. So if something has already been reduced, you can take that because that's common along paths. And the other activity that is reducible is H here, so H by 1. Now if you look at the third path, 22 is less than 25 again by 3. It has an A is already been reduced, and the only activity that now is reducible is K by 1. Now for the other three paths, their original time 22 is greater. Maximum reduction is greater than the original time. 22 is greater than 20 for the next path, and 22 is greater than 19. So when the maximum reduction is greater than the original time, you do nothing. You combine all these together, A by 2, H by 1 and K by 1, and that tells you all the reductions possible, which gives rise to the same answer that we got previously. This is a much easier method. Of course, looking at it and doing a targeted analysis along the network itself is the easiest, but if you want a structure, this method is really easy. Now the reasons why I took A, H and K are because those were the reducible activities, and some of them were on the critical path, and so I took them. I don't take the activities that are not on the critical path unless I don't have a choice. Thank you. Hope you learnt it. Practice is doing, so look at this explanation and then try and work it out yourselves. Thank you. Bye-bye.